IP has two versions, IP version 4 and uses 32 bits for the address, and IP version 6, which uses 128 bits for the address. Most IP addresses are owned by an organization and assigned by the Internet Assigned Numbers Authority, or IANA, as they are responsible for tracking and assigning IP addresses. As I said, IP version 4 IP addresses are 32 bits long, which means there are 32 zeros or ones that make up a binary number for that IP address. We group these binary digits into 4 groups with 8 bits in each of the 4 groups. So, and thus each group is called an octet. The largest possible number we can have in each of the 4 octaves is 255, as we are 0 based. So the numbers can range between 0 and 255 and are separated by a period between each of the 4 numbers. Thus, the numbers in each of the 4 octets, like I said, can range from 0 to 255. An example here is of an IPv4 number is the 72.56.105.12. Right? Each of those numbers has 8 binary digits, and that binary digits, the 8 zeros and ones, are such that they equal the decimal number of, the 72 or 56 or 105 or 12. And once again, they can range between 0 and 255 for IPv4 IP addresses. There are many reserved and special IP addresses that cannot be assigned or used to a device. Also, most IPs are owned by an organization and they cannot be used just by anyone. Right? They are owned by an organization. But there are some reserved IP addresses for private use that anyone can use on their internal networks. And these addresses are called private IPs, and but they cannot be routed across the internet, as they are only valid for internal networks. On this slide, right, so you're seeing the 8 bits, all ones is 255, all zeros would be 0, right? And so thus you're seeing the largest possible IP address then would be 255.255.255.255. And that's all ones in all 4 of the 8 groups, or all 32 bits are set to 1. Here are a few of the special reserved IPs. The 127.0.0.1 is the IP assigned to every network card and allows you to only test your device. And it's called the loopback IP, as you can only send test messages to yourself to verify the TCP IP stack is working on your system. 0.0.0.0 is not assignable and not used. It's currently just not used. The 255.255.255.255 is used, but you can't assign it to anyone because it is the broadcast message, and it means that if you send a message to that IP address, it is broadcast and sent to every device on the local network. It won't go across the router and to other networks, but just your local network. This is how a computer that is configured to receive a dynamic IP address, it will send out a broadcast message to 255.255.255.255 and ask for a DHCP server. The DHCP server will get the message and respond with the information needed to configure the computer, and all other devices will ignore the request. IPv version 4 addresses identify the network and host. The first part of the IP address identifies the network, and the last part of the address identifies the host. To determine what is the network portion and what is the host portion, we use the subnet mask. By using the subnet mask, we can then determine what network an IP address belongs to and what is the unique ID for that device on that network, right? So in this example, the 192.168.80.0 is the network, right? The last 1 through 100 here can represent the host, but technically it would be 1 to 254 on that network by default, but it would be the 192.168.80.0 network, and then the host would be between 1 and 254. With 255 being the another broadcast address for that network. Okay. A subnet mask is 32 bits long, just like the IP address, and every bit is set to 1 in the subnet mask tells you which bit in the IP address is part of the network. The subnet mask and IP address is technically not usable as IP addresses that start with 201 or what are called a Class C IP address, and should have the first 24 bits set in the subnet mask. So here they're depicting that only the first 16 bits are set, but this is inaccurate and incorrect for this IP address, because by default the first 24 bits are set. So this slide is incorrect. This is not a /16, it is a /24. The only way you could use this as a /16 is if you owned all 256 networks in the 201.18 IP range. So you would have to own 201.18.0.0 to 201.18.255.255. You'd have to own all those IP addresses in order for this slide to actually work, because 201 is what known as a Class C address, and so the IANA would not sell you the ability for this. This has to be sold as a /24 address, but we'll just say that it's correct, right? But yeah, you see that the ones start from the left, and they always start from the left for the subnet mask. It tells you what bits are set for the network, and it's a 1-for-1 from the IP address. But you could have a /25, a /28, a /30. You could have a /18, if you have a different IP. Once again, numbers, this 201 is a Class C, and we'll get into that, I think, a little later. And so this should have been 24 ones. The first 3 octets should have been all ones. And then thus the network portion would have been 201.18.20.0, not just 201.18. But otherwise, this is correct. If the IP address were say 150, that's a Class B, which is a /16. So if this was 150.18.20.160, then it would be correct and easy to do and say that 150.18.0.0 would be the network ID, and the 20.160 would be the host ID. But so class A addresses start from or less than 127. So up to 126 is a class A, and that's a /8. 128 to 191 is a /B, or is a B, which is a /16. So 191, as long as this if the 201 were changed to any number less than 192, any number less than 192, this slide would be correct. Because it's over 191, right? So 192 and above to 224, I believe, is a class C address. And then they have some others that aren't used, but A, B, and C are the only ones that are assigned publicly. So this is a class C or a /24 IP address. You could not subnet mask this as a /16 unless you owned all 256 networks in the 201.18 space. You'd have to own all 256 of those networks in order to be able to do this. And even then, I don't know if the devices would actually recognize it. Some of the devices might have issues dealing with this, but it might work. The subnet mask tells us and routers what network an IP address lives on, right? If the device wants to talk with a device that is on the same network, it can easily do that. However, if a device wants to talk to a device on a different network, it must use a router in order to get to the other network. This slide shows that if the device is on the same network, it just sends the message out to the network. And if the device is not on the same network, it sends the message to the default gateway. The default gateway is just another term for router. And just think of it that way. A default gateway is your router on the local network that you send requests that need to go outside the network. Public IPs are owned by organizations and can be routed over the internet. Private IPs are available for anyone to use, but cannot be routed over the internet. They can be routed internally, but they cannot be routed over the internet. The private IP ranges are the 10 network, the 10.0.0.0 through 10.255.255.255. That's a Class A private network. A Class B private network is the networks 172.16.0.0 through 172.31.255.255. Notice that you don't have that many. You only have one Class A network. You have 16 Class B networks, and then you have 256 Class C networks, the 192.168.0.0 through to 192.168.255.255. So you have those three types of private networks. And like I say, you have one A, which is the 10 network. You have 16 Bs, which is the 172.16 through 172.31, and then 256 Class C private networks. And then finally, we have a special private IP address range, the 169.254.0.0 to 169.254.255.255. This is usually used. It is used automatically to assign an IP to a device if DHCP is configured on the device, but the DHCP server is not found or not reachable. You'll see a 169.254 IP address assigned, and what that's saying is you weren't able to find a DHCP server. But if the devices are all configured with 169.254 addresses, you can communicate locally, and it still works. Now, we ran out of public IP version 4 addresses, and thus we created a technique that helped us continue and conserve the numbers of needed public IP addresses, and it's called Network Address Translation, or NAT. And technically, most use PAT, or Port Address Translation, which is just a form of NAT. It allows us the ability to only use a real public address, to use one real public address and then use private IPs for all the devices behind a router. For example, all the computers at TCC use private IP addresses in the 10.0 range, on the 10 network range, but when they go out over the internet, they all share and use the same public IP address. And we use port address translation so that up to 65,536 computers can access the internet at the exact same second using the same public IP address. The router or firewall just keeps track of the conversations and which one belongs to which device by assigning a different port number to each conversation. Here are 3 computers using the same public IP address. And so it's the same concept. The router has the public IP address, the 69.32.208.75, but all the internal computers have a private IP address, the 192.168.40.29 through 31. Those are private IPs. They go through the router, and when they go and access the internet, they show up as the 69.32.208.75. And so thus all 3 of them can share the one public IP address. And this is how we were able to get the IP version 4 to last as long as we were able to. IP version 6 uses 128 bits instead of just the 32 that we used in IP version 4. Leading zeros can be omitted, and if blocks contain all zeros, you can replace them with double colons. However, only one set of double colons can be used. As you can see, you can take the example address and you can combine it or squeeze it, into certain different ways, and then the one with the set of double colons is the preferred method. So that last one is the preferred method. But you can see that the IPv6 addresses are so much more lengthy and harder for humans to deal with versus IPv4, which is why I feel that IPv4 will probably stay on our private networks with the private IPs for a very, very long time, and you just use public IPv6 addresses for the public addresses. I could see that going on and continuing for a very long time, just because the IP version 4 is so much more easy for humans to deal with. So you can see there is IPv6 has 8 blocks in its 16 bits, and IPv6 has twice as many blocks and twice as many bits, which is exponentially bigger, right? So you got the total number of address possibles in IPv4 is just over 4 billion, and the total number of unique addresses in IPv6 is so large we really don't have a number for it. But technically, it's 340 undecillion, 340 quadrillion, 282 trillion, 360 billion, 920 trillions, 938,000 of quintillions, right? I mean, it's just it's insane. That number is just so large. It's unfathomable, and how many IP addresses there are. Not to say that we won't find a way to use them, but for the foreseeable future, seeing how we're barely using IPv6, we have quite a few IPs available. IPv6 terms, right? So link is a local network or network bound by routers. A node is any device that is connected to a network. Interface ID is the last 64 bits of an IPv6 address, i.e. the last 4 blocks. Neighbors, 2 or more nodes on the same link or local network. Multicast address, our packets are delivered to all nodes in a targeted multicast group. Any cast address routers identify multiple destinations, and packets are delivered to the closest destination. Unicast address packets are delivered to a single node. There are 3 types of unicast addresses. The link local unicast, which is used to communicate with nodes within the same link or local network. Link local addresses begin with FE80 and are followed by 64 bits of zeros. The second type of unicast address is a unique local address, which is a private address used when subnetting a private network. These addresses cannot be routed on the internet. These are very similar to the IPv4 private IP addresses, and these addresses start with FD, right? All right. The third and last type of unicast addresses is the global address, which can be routed on the internet. And the first 48 bits of the address is called the routing prefix and is assigned by your ISP. All right. So the link local is just a local address. The unique local address are very similar to our private IP addresses. They start with FD, and then the global unicast are actual unique public IPs, but you will get assigned the prefix from your ISP. And here's that breakdown and their default prefixes. So as I said, yeah, so technically the unique local, right, FC00:7, but today the local addresses, they sign the prefix will usually show FD instead of FC. I mean, it can start with FCs, but nowadays it's FD. The global addresses can be 2000s, and let's see, loop back, like the 127 is 0:1, so it's 127 zeros with a 1. So kind of trying to be the same as the 127 IP address in IP version 4, but this has 127 zeros. So that's our loopback address, just like we had in IPv4. You can use the IP config command from the command line to display your current IPv4 and IPv6 addresses. For IPv6, it generates its linked local IP address by using the network card's MAC address and adds that for the last 64 bits of the IP using the FE80/64 prefix. It then verifies that there is no other device with the same IP on the network, and then checks to see if there's a DHCP server with version 6 IPs with configuration information for it. If there is, it leases the IP and uses the DHCP configuration information. And this is just showing the output of an IP config command. And humans do not do well with IP addresses, so we substitute the IP addresses with human readable names. We have host names, which is the name of the computer. A root group is a group of peer-to-peer computers that are sharing resources. A domain name specifies and identifies a network. Fully qualified domain name is the host name plus the domain name, and it uniquely identifies the computer on the network to which and the network to which it belongs. DNS is the domain name service, and it manages the translations of names to IP addresses and IP addresses to names. And Windows uses the DNS cache to resolve a computer name to IP before it asks a DNS server. So if you've already asked a DNS server and you got the response, you'll store it in your cache, and so Windows will check the cache first before asking a server again. But the DNS cache is just temporary storage of responses to past DNS queries. And so that ends our topic on IP addresses here. Next video will cover TCP, IP, and UDP in more detail.